Okay, now this is additional video for 14.8, the Lagrange multiplier. So what the Lagrange multipliers means. So we already learned on how to maximize functions using some constraint, okay, some function of 2 or 3 variables. Okay. So we are having functions. For example, we have 3 variables functions. So we are going to maximize or minimize the functions, okay? And we have a constraint. We have a constraint in the form of, let's say, function g equal k, or this is we are going to make this g into our level surface. Okay, if we are going to illustrate, this is going to have it to be like this. Okay, so the red color will be our constraint and the blue color will be our functions. So we can have several attempts to check, okay, and each of the level surface will be having a different value for g, okay. So we start by finding, let me write, finding extreme values of the function of xy, okay, with constraint g, xy, and then k. In other words, we are going to we seek the extreme values of f when point xy is restricted to lie on the surface or in the level curve of g equal k, right? So to maximize the function subject to constraint g, is to find the largest value, let's say c, such the level curve of the function intersect the function g equal k. So this is mainly what it means. So we are going to find the value c such that when we have this value, this point will intersect with the constraint which we are having in this one here. So we are going to have the curve on the red curve here, our constraint will touch the functions, So when the functions, or when the c is 10, so this is c, all of this is c, so when c is 10, then we are going to have the functions maximized, okay, with the constraint. Okay, now suppose Suppose function has extreme value at p, let's say x0, y0, z0 on surface S. Okay. And let's see a curve with vector equations xt, yt, zt, okay, and also lies on S and pass through P. Okay. If t0 is parameter corresponding to point P, then the vector will be equal to the point x0, y0, and z0. And the composite function h this will represent values that the function takes on curve C. Since f has extreme value at x0, y0, and z0, it follows that the h has extreme value at t0. So h prime t0 is equal 0 because it's having the extreme value. If f differentiable, then we can write down the let me resize this. Okay, then 0, this will be going to have all partial with parameter t0 at the extreme value. Oh, sorry. It should be having y prime. Okay, and we can write the partial as a gradient vector at x0, y0, z0 dot the r prime t0, the x prime, y prime, z prime. So this is showing that the gradient vector is orthogonal with the r prime. Okay. So the gradient vector f is orthogonal to r prime, and also the gradient of g also orthogonal to r prime. So this means that the gradient vector of f should be parallel with gradient vector of g, and thus this will resulting in what we call the Lagrange equations. So we will have, so if the gradient g is not 0, there is a number that we call lambda, or we call this is the Lagrange, okay, such that the gradient factor of x0, y0, z0 equal with the lambda or Lagrange multiply with the gradient factor of g. Okay, the number lambda, we call this is the Lagrange multiplier. Okay, so to find max or mean values of f with constraint g, where the gradient g is not zero, and assume extreme value exists, then first find all values that's possible of x, y, z, and also the Lagrange multiplier, such that the formula applicable and we will have a constraint for restriction of the value itself. And then the second one, evaluate all the points, evaluate the function f at all points, and then arrange the max and min. Okay, that's how we are going to set our equations. Okay, let's try some example. So if, for example, if f, so the one that we are going to evaluate, this having 3x squared plus y squared minus 2z squared, okay, and has a constraint, so has a constraint. So this will be f, this will be g, okay? So we can write the f is our functions here, and this will be our g, and we can write 3x plus 3y minus 8z. Now we can start by building our Lagrange. Okay, we built this, and we start by each of a component, so component of x and component of y, and component of z. So So we are going to solve the equations, finding the either the x, y, z first or the lambda, the Lagrange first. But let's just write all partials. So the partials will be 6x equal to lambda 3. This will be 2y with lambda and 2. This will be 4z or minus, okay, with lambda and negative 8. So this will be resulting in lambda over 2, y equal lambda, and z will be 2 lambda, right? Now we have our constraint, right? G. We can write the constraint and then exchange all with the lambda, so we can find the Lagrange first. Now we can solve this, find the lambda, that is 100 divided by 25, which is 4. Now we have lambda is 4, then we have x, 4 divided by 2, y from here, this is 4, and z will be 2 multiplied by 4, it's 8. So f 2, 4, 8. If we plug in into our equations, 3, this will result in negative 100. And if you check other numbers, you can argue that this will be our minimum values. Okay. Okay, another example that we can find. Okay, if I have this is we already start using 3 variables, but let's start with 2 variables first. Find extreme value of the function. So we can see that this is the constraint, right? The x squared plus y squared equal 1 is a constraint, and we are going to find the extreme value of the function of 2 variables. We are going to take our Lagrange. So take the partial x, partial y, partial z. Oh, sorry, no z. Okay. From here, we got that lambda is just 1. And we get the x squared plus y squared is equal 1. Or we get this precisely, okay, precisely, sorry. This should be written as so x equals 0 or lambda equal 1. If x 0, then y will be plus minus 1 from x squared plus y squared equal 1, right? If lambda is 1, then it will give that 4y equal 2y, or or y is equal to 0 here. And then, because of y equals 0, then x will be plus minus 1. So we have at least from this 0.1 point, this is 1, 0, 0, -1, and then -1, 0. So if we check all these 4, so the 4, how we can get this 4 is from x0 we have to y plus minus 1. If we have y0, we have plus minus 1 for the x. Now we check all these points. So we check the x squared plus 2y squared. So check this one is equal to the 0, -1 is also 2, 1, 0 will be 1. This is also 1. So this will be the maximum value, this will be the minimum value. Now if we look on how it's actually described, if we check the surface itself, this is our constraint. This is our constraint, and this is our functions. So what we are doing is actually we are going to maximize the blue color here to touch the red one. So we are touching the red one is around what here. Okay, and when this is happen, we know that this will be equal to what we have here, 2 and 1. So this is 1 and this is 2. Okay, so this will be the point. This is a 1, 0. This is -1, 0. This is 0, 1. This is 0, -1. Right? This is the 4 point we have. Okay. I hope you can get the notions or the applications on how we can use the Lagrange multiplier to maximize or to find the extreme value of the functions, and how we can use the Lagrange whenever we find a function that we are going to optimize, and the functions or a constraint that the questions given when it is give you some information about the constraint, then you can directly apply the Lagrange multipliers. And aside for this is just a one constraint, right, on the G. Well, we can also have multiple constraint, or at most it's 2 constraints. So 2 constraints. Well, it's actually similar. So we are going to include another gradient factor and another constraint. So we are going to involve the first constraint is G, the second constraint is H. So we are going to have 3 gradient vector. Okay, so 3 gradient factor that we are going to maximize or minimize, so that the gradient factor or the curve itself will be touch the level curve of G and level curve of H. So we are going to have, I will directly write the conclusions. That is Now it's called lambda gradient g at that particular point that we are going to find. And also we call the second constraint as the mu, the Lagrange. This is h, x0, y0, z0. And to solve this, it's a little bit takes time because we have two constraints. Okay. For example, let me start with f x y z, x plus 2y plus 3z. So find maximum value of f on curve of intersection of plane, of plane x minus y plus z, and cylinder for now. How it looks like, it doesn't really matter, but yeah, maybe later I will show you. I think we can still a little bit draw this part. So maximize f with constraint g and h. So we will have a gradient factor okay, and we can try to solve this gradient factor. So for partial x we have 1, and then we have lambda plus 2x. This is for x. For y we will have 2. This will be negative lambda plus 2y mu. And for z, there is only for f, so this will be 3, and this should be equal to lambda. So lambda is equal to 3, and we'll have x minus y. Oh, sorry, this should be equal 1. X minus y plus z is equal 1. X squared plus y squared is equal 1. So this is the constraint. So we have lambda is 3, and we are going to use this lambda inside this mu, so we can get the 2x mu is minus 2, so x is minus 1 over mu. And similarly, we take the other part, 2 minus 3 plus 2y mu, so we will get y equal 5 over 2 mu. And if we substitute and take into this circle equations, we are going to have equal 1. So we can get that the mu squared is 29 over 4, or mu is half squared of 29. Now x will be negative 1 or 2. I think that's our x. And it should be plus minus, because it should be plus minus. Okay. So y also can get the notion of 5 divided by square root of 29. And then we can use this to take into our function. So f x plus 2y plus 3z. So f will be equal plus minus 2 over and plus minus 2 plus 3 plus minus z. Okay, z should be going from here, so we can take z. Well, anyway, let me just erase this first and write z first. Z is 1 minus x plus y, and check with the x here, y here. So you'll have at least several x, y, and z. You can check all the terms for x, y, z, and then you can find which one is the maximum value. Okay, but that's how we can apply the Lagrange multiplier. I think that will be the end of this sections for Lagrange multiplier. We can have more example in the future. Okay, but that's the basic one for Lagrange.